Okay, what method are we going to learn? We are actually going to be learning 3 methods. They all start with finite. There are methods that doesn't start with finite, but like here we have finite difference. This is the most basic method, and if you have a simple domain, which means the geometry of the domain is simple, which is always the case in 1D, finite difference is usually a great choice. We also have finite volume, and the finite volume is primarily good at dealing with a very complex domain, but it is pretty restricted in what kind of equations it can solve. And a lot of computational fluid mechanics uses finite volume. And then there is this finite element. Finite elements is the most complex methods to use. It's also one of the most flexible method to use. And finite element can also handle very complex domain, and it is right now the most popular method in structural mechanics. Okay, so we're going to be learning all of these 3 starting from finite difference. And how does finite difference work? Let's see. Again, I'm going to start with some demos. So I have a FD demo. I'm actually having demo of all 3 types of method. And today I'm just going to show you the difference between 2 methods, finite difference and finite volume. So for finite difference, finite volume, finite element all require a mesh. A mesh means I have a way of discretizing space into a finite set of in one-dimensional segments, right? And I need to ask again somebody to draw me some functions, and we are going to see how finite difference and finite volume approximates your functions in different ways. Somebody come and draw functions. You're drawing good functions, very creative. So please. Come on. All right, cool. Thanks. So let's watch how finite difference discretize your equation. Your equation, yeah.
Any function?
Any function, yeah.
Wow.
All right, thank you. It's a good function. So here, the original function is still shown in red, but like the points are what finite difference actually keeps track of. So if you use finite difference, you don't care what's actually in between these grid points, right? You only care about what is the value of the function at these points. You don't care anything between. It's very different from finite volume. So somebody come and draw a finite volume function, FV finite volume function. So I'll keep this to be here. Oh, wait 1 second. Oh, this actually, well, I actually automatically discretizes your same function with finite volume, right? So you have the same function. This is how finite volume discretizes the same function. See how is it different? So what does finite volume do? Yeah, it focuses on the segments instead of the points, right? It tries to keep track of what is in between the points. And how exactly does it keep track of the information in between the points? It's just the average, right? I mean, a computer can only keep track of finite number of things, right? And the function in theory is infinite dimensional. So you have to discretize it somehow. You have to use finite number of things to approximate a function. Finite volume focuses on the segments and keeps track of the average in the volumes, while finite difference forget about what's in between the points and keep track of only the information on the points. Right, both are valid methods of approximating the function. One of the things to remember is that in finite difference, we are having a grid from 0 to 1.2, so basically 10 intervals. How many values does finite difference keep track of? Well, I'm asking almost trivial questions, but when you guys are writing a code, one of the most common errors is indexing bugs, right? How many points I have? In this case, I have n intervals, n equal to 10. How many points do I have? N plus 1, right? We have n plus 1 points. So, I mean, the indexing is important. Now, it's actually a bit more tricky than that. If I have periodic boundary conditions, right? I mean, this is not periodic boundary condition. But if I have periodic boundary condition, this point is the same as this point. So I have one less degree of freedom. I got rid of 1 point. I only have 10 points. So finite difference, the indexing actually depends on the boundary condition a lot. Another case, if I fix the boundary condition here, if I know the left boundary, the function is equal to 0, then I lose actually 1 degree of freedom on the left. Again, I get 10 points. If I have no boundary condition on either side, I have 11 points. If I have 2 boundary conditions on both sides, I only have 9 points, right? So finite difference, the indexing is a little bit tricky. Unlike finite volume, if I have finite volume, then no matter what I do, I have 10 values to keep track of, right? Independent of what boundary conditions I use. All right. So finite volume is what we're going to be studying next, later. But finite difference is what we are going to be studying immediately.